Good morning, ladies and gentlemen. My name is Fatih Tarada and I work for Mosen Limited, which is an engineering consultancy. Today, I'd like to speak to you about deflectors for tunnel jet fans. So what's the motivation for our research? It's a two-pronged motivation. The first issue we want to address is whether deflectors do indeed improve the internal thrust. And the other issue is whether the effect of deflectors on bench thrust, noise, power consumption, service life and tunnel environment are significant or not. So, here are the contents of my presentation. First of all, we will address the issue of internal thrust. In other words, what will the effect of the deflectors be on the thrust within a tunnel? And then we move on to the issue of bench thrust, which is what is the effect of the deflectors on the thrust that we would measure in a factory. And then we will look at the issues of noise, power consumption, structural integrity, jet throw, and then move on to conclusions. So, first of all, the issue of internal thrust. Well, the whole point of using deflectors is to reduce the Coanda effect and thereby increase the thrust of a jet fan in a tunnel. The Coanda effect is simply the effect whereby a jet discharged by a jet fan sticks to the neighboring tunnel surfaces, for example, a soffit or a sidewall, and the friction due to that adherence of the jet to the tunnel surfaces causes the overall thrust or the internal thrust to be reduced. So the more we can peel off that jet from the sidewalls and the soffit, the more thrust we can actually generate. So there's been a number of research projects, for example, Lutzberg, 1997, and Baer et al., which is Austrian work done in 2016, which showed that deflectors can indeed be effective in turning the discharge flow and in increasing the tunnel air velocity. And in particular, the researchers from Graz University in 2016 showed that we can increase the internal thrust by up to 20% with deflectors. So here are some images from that research work in 2016, which were undertaken in Bosrup Tunnel in Austria. Both physical measurements and 3D computational fluid dynamics undertaken using ANSYS CFD. And as you can see, one of the main issues in the Bosrup tunnel is that the jet fans were installed quite close to some head walls, and it was necessary for the jet to actually miss the head wall in order to reduce form drag and thereby increase the air velocity in the tunnel. And that they managed to do with these deflectors. So that is their conclusion. What we did was we undertook a series of experimental measurements on a 710 millimeter internal diameter jet fan with a two-pole motor running at nearly 3000 RPM. The blade pitch angle was set at 32 degrees, and we had 1D silencers installed on both sides of the jet fan. The deflectors had curved vanes, and they were installed either on one side of the jet fan or on both sides. And we also tested with both rectangular and circular deflectors. So, in terms of the bench thrust results, which were measured in a factory, you can see what the results are in accordance with ISO 13350. And we've plotted them as a function of distance from the silencer to the deflectors as a ratio of jet fan diameter. So as you can see, when you install the deflectors with no distance between the silencer and the deflectors, in other words, the horizontal axis 0, you can see that the bench thrust reduction can be up to 20%. So that's over here somewhere. Yeah, almost 20% reduction. Whereas when this distance increases, that reduction then subsides or reduces, so you can end up with something of the order of 10% or so reduction, which is around there. Okay. However, it's clear that even if you do install the silencers or the silencer to deflector ratio of around 0.4, you are still suffering from some loss in thrust. So it's certainly significant and cannot be discounted. The other issue is whether different types of deflectors can actually influence the amount of loss of thrust that we'd experience. So we tested this both with rectangular deflectors and with circular deflectors. And what you're seeing here is the result for a distance ratio of 0.4, distance divided by jet fan diameter of 0.4. So in this case, you can see that there's not a lot of difference whether you have rectangular or circular deflectors. The loss is in the range of kind of 6 to 10%. If we now move on to the issue of regenerated noise. So if you can imagine, there's a high-speed jet being discharged from the jet fan and it's striking the vanes. And because you've got this high velocity jet of between 30 to 40 meters per second, you will have a significant amount of regenerated noise because of vortex shedding behind the vanes and also because of mechanical vibration of the vanes themselves. So, how much regenerated noise? Well, if we install the deflectors right up against the silencers, then we can expect an increase of in the range of say 3 to 5 dB, as you can see here in this left-hand side. And that tends to reduce if we increase the distance from the silencer to the deflector. However, it reaches some kind of optimum at a ratio of 0.2, and then after that it starts to increase again. At the moment we don't know exactly the reason why there is this optimum, but it could be that there is some kind of effect whereby the vanes are excited by the air velocity that's striking them, and once you move them to a certain extent, that kind of resonance phenomenon subsides. The other issue to think about is power consumption, because when you install deflectors on jet fans, you tend to increase the power consumption, sometimes quite significantly. So if you install the deflector right up against the silencers, then you are going to get an increase in power consumption of around 10 to 12%. Obviously, if you increase that distance, then you are reducing the power consumption, but you're also reducing the effect of the deflector itself, clearly, because you may lose some of that deflection performance. However, you can end up in the range of kind of 2 to 4% power increase for a distance ratio of about 0.4, which is around here. Again, if we look at the issue of whether different kinds of deflectors have different performances, well, it appears that there isn't a great amount of performance difference, and all of these results are shown with a distance ratio of 0.4. That is the distance between the silencers and the deflectors divided by the jet fan diameter. And it doesn't seem to be a huge amount of difference whether we go for circular or rectangular deflectors. If we do install deflectors on our jet fans, then there is a risk that these deflectors might suffer from fatigue-induced failure and break off, because the vanes are excited at their natural frequency or multiples thereof, and because they're excited at these natural frequencies, they will vibrate and eventually they might actually break off. And in order to assess that, it's necessary to refer to relevant standards, for example BS 7608, which is the Guide to Fatigue Design and Assessment of Steel Products, and in particular to the welds that are applied to such products. If we do indeed have a failure of these blades, then they might actually fall onto the moving traffic below, and that clearly presents a safety risk to the motorists and to anyone else in the tunnel. So therefore, fan manufacturers, installers, consultants and tunnel operators may all be liable for any injuries or deaths, and that's even after any warranty periods for this product have expired. This is a very important issue. It's nothing to do with warranty periods. You may still be liable for any injuries or deaths. And for that reason, i.e. the safety reason, it's very important that where we do specify deflectors, that they should have a significantly longer fatigue life than the mortar bearing life. So for example, if the bearings are specified to 20,000 operating hours, we should be specifying the deflectors to at least 100,000 operating hours. And also, when we get into the tunnel and inspect our fans, we need to look at the deflector vane joints on a risk assessed basis, because we need to check whether there indeed has been any damage and whether any cracks might be propagating and causing premature failure. So we need to go in there regularly and check whether there's any damage that has occurred. Now, the other issue to think about is the issue of swirl. In a conventional jet fan, such as the one shown in this image here, what typically happens is that we are drawing the air from one side, we're discharging it on the other side, and on the discharge side, we normally have a large amount of swirl. And that swirl is actually doing us a lot of benefit, because it's actually mixing the discharge jet into the airflow, the tunnel airflow, in a very short distance, and it's imparting its axial momentum that way. Now, what happens if we put a deflector on the discharge side? Well, the deflection vanes actually kill the discharge swirl and therefore significantly extend the jet throw. And it does that in a way that's actually quite damaging to what we're trying to achieve. So, if you look at the experimental measurements of swirl on jet throw as measured in diffusers, so on the left-hand side, you've got the situation without discharge swirl, in other words, with these deflectors, and the one on the right-hand side is with discharge swirl, which would correspond to a conventional jet fan. And if you compare the two sets of figures, you can see that actually the jet throw can be extended by more than 100% through the addition of deflectors. So we really are extending the jet throw very, very considerably by installing these deflectors. And the effect on internal thrust due to that extension of the throw can be quite dramatic. So what you're looking at here are results from our 3D CFD analysis, which we undertook on a jet fan with some deflectors installed at 0.5 the jet fan diameter downstream and upstream. And what's happening here is that the swirl is present at the discharge from the jet fan, but the moment that it strikes the deflectors, the swirl is killed, it's no longer there, and therefore what you have is just a planar jet which doesn't mix very well with the tunnel airstream, and eventually it just adheres to the tunnel floor right there. There's the attachment point, and then it just continues onwards as a floor jet. And of course, there's clearly a lot of friction going on right here at the interface between the jet and the tunnel floor. And because of that, we dramatically reduce the installation factor. So we calculated that the installation factor is going down in this case from 0.84 for a conventional jet fan to just 0.6 for a jet fan with deflectors. So in this case, our original idea to increase the installation factor and to enhance the internal thrust has actually gone terribly wrong, and we've actually managed to reduce it. So that's something to bear in mind when you specify these deflectors. They can actually work against you. The other issue with deflectors is that because we're killing the swirl and we're extending the jet throw, we can actually have a situation where the jet can actually stick to high-sided vehicles, for example, heavy goods vehicles and buses. So they can be buffeted due to the forces of the jet. And of course, we can also reduce the effective thrust because we're increasing the shear, the aerodynamic shear between the jet and these vehicles. If we have got any people in the tunnel, any pedestrians or emergency responders, for example, the fire brigade, they might be subjected to some quite high air velocities, perhaps in excess of the recommended 11 meters per second maximum. So that's also something to watch out for. So in conclusion, so theoretically, deflectors give us the option or the potential of increasing the internal thrust, but paradoxically, they can actually reduce the internal thrust because they can certainly reduce the bench thrust, which we measure in the factory. They certainly increase the noise production. They require higher power consumption. They're associated with the risk of structural failure due to fatigue. And of course, they might certainly extend the jet throw, causing the buffeting of vehicles and pedestrians during use. And I just want to end with this image of our recent successful MoJet test in the Queensway Tunnel. So with the MoJet, this product gives us the advantages of the deflectors in terms of turning the flow and reducing the Coanda effect and enhancing the air velocities in the tunnel without any of the disadvantages of the deflectors. So thank you very much for your attention, and I look forward to your questions.